Okay, let's try another area problem. We want to find the area inside the graph of r equals 8 sine theta and outside the graph of r equals 4. Now this one's a little bit tricky because we haven't been given limits of integration and we're given two different functions. So somehow we have to figure out what those functions look like and also figure out the limits of integration ourselves. R equals 4 is probably the easier one, so I'll start with that. That's just all the points at radius 4 from the origin, so that's just a circle. R equals 8 sine theta is a little bit trickier. If you graph y equals 8 sine x, you get an exaggerated sine curve that goes up to 8 and down to -8, comes back to 0 at pi, and again at 2 pi. If you graph r equals 8 sine theta, that starts out, when theta is 0, it starts out at 0. When theta is pi over 2, it goes up to 8. So that's 8. When theta is pi, it's come back to 0. When theta is 3 pi over 2, it's gone to -8. So it's just, let me show this in blue, it's just retracing itself again. And when theta gets to 2 pi, it's come back to 0. So that's what the graph of r equals 8 sine theta is. Its intercept on the pi over 2 axis is 8. And I want to show those two graphs together. Remember, r equals 4 had a radius of 4. So let me put that graph on there. So we're actually looking at two circles here, and we want to find the area inside the graph of r equals 8 sine theta, outside the graph of r equals 4. So let me try to color that area in red. That's the area that we're trying to find, which means we have to figure out where those two graphs intersect and then integrate from one intersection point to the other. So to figure out where those two graphs intersect, I'm going to set them equal to each other. 4 equals 8 sine theta, and that means 1/2 equals sine theta. And there's two angles that have sine 1/2. Theta equals pi over 6 and 5 pi over 6. And you can kind of see that in the picture. This is pi over 6, and this is 5 pi over 6. So what we're going to do is integrate using our area formula. I think what I'm going to do is just find 1/2 of this area. So I'm just going to find that segment. I'll color that in black. I'm going to find that area, and I'll multiply it by 2. So I'm going to integrate from pi over 6 to pi over 2. Pi over 6 to pi over 2. Now I want to find the outside area minus the inside area. Well, our formula for area is f of theta squared over 2. Here, the outside area is 8 sine theta, or the outside curve is 8 sine theta. So I'm going to find 8 sine theta squared over 2. That's the outside area, minus the inside area is just 4 squared over 2. That's what I'm going to integrate. And that's kind of nice because the 2's cancel right away. So we get the integral from pi over 6 to pi over 2 of 8 sine theta squared, so that's 64 sine squared theta, minus 4 squared is 16. Remember, the 2's canceled with the 2 on the outside, d theta. And so that's the integral of, well, sine squared theta. We're going to use a half angle formula to deal with that. Remember, sine squared is 1 minus cosine 2 theta over 2. So 64 sine squared theta is 32 times 1 minus cosine 2 theta. And we still have minus 16 d theta. And so here we have 32 minus 16. I'll put those together and just get a 16 minus 32 cosine 2 theta, just 16 theta. Now the integral of cosine 2 theta is sine 2 theta divided by 2. So the integral of 32 cosine 2 theta is 16 sine 2 theta. And we said we wanted to integrate this from theta equals pi over 6 to theta equals pi over 2. So we're going to plug those bounds in. We get 16 times pi over 2 minus, now if we plug pi over 2 into sine of 2 theta, that's giving us sine of pi, so that's just 0, minus 16 times pi over 6, which is, I'll just leave that as 16 times pi over 6 for now, plus 16 times sine of 2 times pi over 6, which is the sine of pi over 3. We can simplify this. Pi over 2 minus pi over 6 is pi over 3. So if we combine those two terms, we get 16 pi over 3. Now the sine of pi over 3 is the square root of 3 over 2. So 16 times the sine of pi over 3 is 8 square roots of 3. So we get our answer 16 pi over 3 plus 8 square roots of 3. So this problem was pretty tricky, but it was really the geometry that made it tricky and not the calculus. We were given two curves and we weren't really told how to handle them. So the good thing to do is to start out by graphing the two curves, putting them together on the same graph, and then trying to find these intersection points. We actually found the intersection points algebraically by setting the two equations equal to each other. Once we found the intersection points, that gave us our bounds on the integrals, and then we used this area formula. Remember, the area was f of theta squared over 2 d theta. But since we had to find the area between two curves, we looked at the area of the outside one minus the area of the inside one, and then we worked out the integration and we got our answer.